General procedure for design of simply supported one-way solid slab to BS8110 with example. Steps. 1. Determine a switchable slab depth. You can easily estimate it by using the formula stated below, which is effective depth is equal to span over basic ratio times modification factor. For a simply supported design, the basic ratio is 20. You can find out on table 3.9, page 35 of BS8110 part 1, 1997. This book is available through a link in the video's description. You can start with an initial modification factor of 1.4. Note that your slab thickness must satisfy deflection requirements, otherwise you will have to redesign. Ways to make your design satisfy deflection requirements if failed initially is either to increase slab thickness or increase amount of reinforcement or both. Number 2, calculate the main and secondary reinforcement areas. You can do this by using the formula stated in the BS code. Details later. Number 3, check for excessive deflection. As stated earlier in number 1, your design must satisfy deflection requirements. Detailing. For economical arrangement of steel reinforcement, you can refer to clause 3.12.10.3 of the BS8110 code. Now, explanation of other important points in solid slab design to BS8110. Now, let's look at the effective span of the slab. Referring to the diagram above, the effective span of slab, which is referred to as L, refers to A, the distance between centers of bearings, or the clear distance between supports, D, clear distance between supports represented by D, plus effective depth D of slab, plus the effective depth D of slab. Calculating steel areas. In calculating the slab self-weight, the overall depth of the slab referred to as H should be used. H is the effective depth of the slab plus allowance for cover to reinforcement plus half the assumed main steel diameter. So D is effective depth, H is overall depth of the slab. Now C is represented as the cover to the reinforcement, which is shown here, and then we have this represents the diameter of the reinforcement bar shown. The self-weight of the slab together with the dead and live load is used to determine the design moment M. The value of M must be checked against the value of MU, which is the ultimate moment of resistance. So MU, referred to as the ultimate moment of resistance, is equal to 0.156 FCUBD squared, where B is 1000 millimeters. Why? Because slabs are designed in series of 1 meter width, and FCU is referred to as the strength of the concrete. Now, if MU is greater than or equal to M, then the slab doesn't need compression reinforcement, which is usually the case for slabs. Now, main reinforcement areas. The area of reinforcement, AS, can be determined using the formula AS is equal to M divided by 0.87 FYZ, where M is design moment, which is, for a simply supported slab, is WL squared over 8, and W is the design load of slab in kilonewton per meter squared, L is the span of slab in meters, and Fy is the strength of steel. Now Z, which is referred to as lever arm, you can see the formula, that is stated, into D, into bracket 0.5 plus square root 0.25 minus K over 0.9. And we have K is equal to M over FCU BD squared. These are just standard formulas stated in the DS code, so take good note of that. And now, going back to the area of reinforcement AS for the main steel, we can see an 0.87 here. In the latest BS code, it's 0.95. So, whichever one you want to use, it's okay. Secondary reinforcement steel areas. Secondary reinforcement also refers to distribution steel. As per BS8110, it is calculated as follows. AS minimum is equal to 0.24% of the area of concrete section of slab, where Fy is equal to 250 Newton per millimeter squared. And AS minimum is equal to 0.13% AC, when Fy is equal to 460 Newton per millimeter squared. Note that the area of tension reinforcement should not be less than the values calculated from the relevant equation stated above. As per reinforcement detailing, see curtailment rules below for a simply supported slab. Now, for a simply supported slab, we have 100% of the reinforcement considered at the center of the slab, and then towards the side, the area of reinforcement can be reduced to 40%. Check that your slab design meets deflection requirements. So after calculating the areas of steel for your slab, you need to use some formulas to determine if it satisfies deflection requirements. So the first thing you do is to calculate the service stress, Fs, using area of steel required and area of steel provided, using this expression. You can find it in the code. Modification factor can be found using this expression. Now, this MF that you will calculate is your actual MF, since it's a function of the area of steel calculated and the area of steel provided. So, if the assumed value of D is greater than the actual D, then deflection requirements are satisfied. Crack width. BS code specifies that crack width should not exceed 0.3 millimeters. Except by calculation, the following rules should ensure crack width requirements are satisfied. So, when Fy is mild steel, which is equal to a strength of 250 Newton per millimeter squared, and depth of slab is less than or equal to 250 mm, or Fy is equal to 460 Newton per meter squared, and depth of slab is less than or equal to 200 mm. So if you are using high-yield steel and your depth of slab is less than or equal to 200 mm, then you don't need to worry about crack width, it's already satisfied. Maximum bar spacing of reinforcement. Now, referring to the diagram shown above, BS code specifies that the clear distance between tension bars should be less than 3D or 750 mm, whichever is the lesser. So, this is the tension bar in section. These are the tension bar spacing in the plan view. So, the distance between the spacing between tension bars should be less than 3D. D is the effective depth of the slab. Now, example design of a simply supported slab. Now, from the diagram of part of a floor plan shown on the right, this is it. I will be designing the panel labeled A, panel A. The first thing to check is see if the slab is a one-way or two-way slab. Now, by observing the dimensions relating to the slab panel, the longer side is 5213 mm and the shorter side of the panel is 2375 mm. So, to calculate the shorter side, looking at the dimensions given here and here. Now, therefore, longer side divided by shorter side is equal to 5213 divided by 2375, which is 2.19, which is greater than or equal to 2. Therefore, panel A is a one-way slab. This means that the main reinforcement bars will span along the y-axis, that's the shorter side, and the distribution bar will span along the x-axis, the longer side. So your main bar will span across along the shorter side, and the distribution bar will span along the longer side. So for a simply supported slab. Note that in a one-way slab, the span of the slab is the shorter side. The span of slab panel A being designed is 2,375 millimeters. Further observation of the slab panel will show that its thickness, that is the overall depth of the slab, has been given as 150 millimeters. Let's see, 150 millimeters. So when we look at this here, 150 millimeters. Your duty as the designer is to calculate the required steel reinforcement and check if the design satisfies deflection requirements. If the slab thickness wasn't given, then you are free to assume a thickness and check that it works. Parameters. Weight of concrete is 24 kN per meter cubic, and strength of steel Fy is equal to 460 Newton per millimeter square. Now calculating the design load. The formula stated by code is 1.4 GK plus 1.6 QK, where GK is dead load and QK is live load. Mind you, the BS code is available through a link in the video's description. So GK is equal to dead load and QK is equal to live load. Dead load is the self-weight of the slab plus finishes. The live load refers to variable or movable loads such as people, furniture, etc. The slab carries. Live loads for different categories of building are stated in BS8399 Part 1 1997, which is also available through a link in the video's description. GK is equal to weight of concrete times slab thickness. So, and which is equal to 24 kN per meter cubic times 0.15. 0.15 is referred to as the thickness of the slab, which further gives us 3.6 kN per meter square. So when we add finishes of say 1.2, it gives us a total GK of 4.8 kN per meter square. So GK is estimated as 4.8 kN per meter square. Now for private dwellings, QK is equal to 1.5 kN per meter square, see table 1 of BS8399 Part 1 1997. So now we go on to calculate the full design load using the formula stated here, and so it is calculated as 9.12 kN per meter. 9.12 kN per meter squared per meter width. Slabs are designed per meter width. So that's the design load. Design moment M is equal to WL squared over 8, where W is equal to design load and L is equal to span of slab. So W is now calculated as, using this formula, to be 6.43 kN meter. Now we are going to check the ultimate moment of resistance, which is equal to 0.156 FCUBD squared. So where D is effective depth of the slab, which can be estimated as the overrep depth of the slab minus concrete cover to reinforcement minus half of the main steel diameter. And when we use that, assuming we are using a main steel of 12 mm, we get 119 millimeters. Remember, this is 150 refers to as the overall slab thickness, 25 mm is the concrete cover to the reinforcement, and 6 mm is half the diameter of the main steel reinforcing bar. So we have explained it here. B is equal to 1000 millimeters. Slab are designed per meter weight, and FCU is equal to 25 Newton per millimeter square, which is strength of concrete. Strength of the concrete mix. So MU, calculated using this expression stated earlier, will give us 25 0.23 kilonewton meter. Please, when you are doing this work, always take note of the units. The units are very important, or you will run into a lot of trouble. And when you are doing calculations of this nature, use a standard scientific calculator. It's going to help you a lot. Now, since M is less than MU, no compression reinforcement is required. When we look at what we calculated at M and this, find out that M is actually less than MU. Now we go further. After calculating M, we go further calculating K, and K is calculated using this expression. We already know M, we already know FCU, we know what B is, and we know what D squared is. So slotting those values into here will give us 0.0182. And then we can now go on, after finding K, we will go and find the lever arm with Z, which using the expressions of K and D, we get 116.54 millimeters. Now there's a limiting. It's limited to 0.95D. So we're going to check it. Now, limiting to 0.95D, we have 0.95D to be 113.05. So since this is greater than this, we are going to use this value instead of this value, because that's what the code states. So use Z is equal to 113.05 millimeters. So hence AS is equal to M over 0.87 FYZ. We know M, our design moment, to be 6.43 times 10 raised to the power 6 Newton per millimeter square, and then 0.87. We know our Fy to be 460 Newton per millimeter square. That's the high yield steel, and then our Z, which we have calculated. So AS required is from this. Putting those values into these formulas, we get 142.12 millimeters squared per meter width of the slab. So now we're going to look at the bar size table. So from figure shown to the right, use Y10 bars at 200 mm spacing as main steel reinforcement. So when we look at it, 142.12, let's see it. 142.12. When we look at it here, it falls under a bar size of 6, but then we can increase it, because in reality we shouldn't be using a bar size of less than 10 for our slab reinforcement. So we'll be looking at one that looks economical to us, and then we must make sure that it goes above the minimum steel required that is stated by code. So let's take Y10 at 200 centers, which is 393 millimeters squared per meter. So Y10 at 200 AS provided will now be 393 millimeters squared per meter. AS provided was what? AS provided is 393 millimeters squared per meter, and AS required is 142.12 millimeters. Remember, this you are going to use to check for the deflection later on. Now for distribution reinforcement, minimum steel reinforcement specified by code is 0.13% BH, because we are using a high yield steel. So when we calculate it, we have a minimum area of 195 meters squared per meter. And so looking at the chart again, we can select a steel of Y10 into 250 bars. Now you are free to choose steel area of your choice, but you must make sure that you are very economical with your design and make sure that those steel areas are available. Now note that the calculated required reinforcement is less than the minimum reinforcement specified by code. Now what we calculated initially for the main reinforcement is less than the minimum. So in that case, the minimum reinforcement specified by code supersedes and should be used to select provided steel. Also, using Y10 200 as main and discarded reinforcement steel is okay. It's your design, you're in charge. Just make sure you follow the code requirements and design, laying emphasis on economy. Now we are going to check for deflection. The service stress using the formula stated here, using the area of steel required and area of steel provided, you can see we have 110.9 Newton per meter squared. And then we go on to use it to calculate the MF, which we get as 2.8. But remember, in the code, it's also limited to 2. So since 2.8 is greater than or equal to 2, we are going to limit our MF to 2. Hence, MF is equal to 2. Now we are not going to calculate the D minimum required, which is span over basic ratio times MF we just calculated. So doing that, we get 59.375 millimeters. And if you look at it, this is much less than what we have been using so far, which is 119 millimeters. Hence, deflection is fully satisfied. Crack width check. Since the slab is less than or equal to 200 mm, crack width check is satisfied. Maximum spacing check. The reinforcement spacing of 200 mm for steel and 250 mm for dispersion is less than, of course, 3D. So you'll see how it was calculated. Hence, maximum spacing check is also satisfied. Now, let's look at an explanation of the detailing. Now, this detailing is just for you to know, it's just an explanation. It's not the way you present it as a detailing when you are doing it in real life. So there's a standard way of doing it, and the link to that is also available in the video's description. So now we have our main steel as Y10 at 200 centers, and the area of steel is 393 millimeters squared per meter. And we have our distribution steel now as Y10 250 centers. So an AS is equal to 314 millimeters squared per meter. So now let's look at the section of the slab panel. Now in this section, look at the span of the slab, which is 2,275 millimeters. Now look at the main reinforcement represented by the black line here, the main reinforcement, and and it's also shown in the plan, spaced at what? 200. There are 27 of them. That's why you see the 27 spaced at 200. Spaced at 200. So the main bar span along the span of the slab, which is 2375 mm. Remember, the span is the shorter side of the slab, and it's represented in the section here. And so the dispersion reinforcement too consists of 10 in number, and you know how that 10 was gotten from? This is the dispersion reinforcement here. 10 in number, that is 250 centers divided by 2,375 mm divided by 250 centers to get 10. The main steel was 27, which is 5,213 divided by 200 plus 1, or to the nearest whole number. Okay, so this is an explanation of how you detail. It's just for you to understand it. There's a standard way of presenting it, which you should learn as a separate course. Thanks for watching this video. If you like this video, please support my channel by liking it and subscribing if you have not done so. Don't forget to check the link, the video description. There are many goodies there, including the RCC spreadsheet for design of reinforced concrete structural elements to BS8110. Thanks for watching. Bye for now.